Question. Let S be the upper half of the ellipsoid 4x squared plus 9y squared plus 36z squared equals 36. So the fact that it's the upper half, we're talking about z greater than or equal to 0. And let's take that surface and orient it upwards. So oriented upwards. So let's let capital F be the following vector field. So y comma x squared comma quantity x squared plus 4 y to the fourth, excuse me. Let's write that better because y looks like 4 here. Y to the fourth quantity to the 3 halves power times sine of e to the root xyz. Okay, this third component is quite a mess. The question here is to find the double integral over the surface that was described here of the curl of the vector field dot ds. Okay, the fact that curl of f is here instead of just f alone is suggesting maybe we look at Stokes' theorem instead of, I mean, you can always look at the problem and just try to set things up directly, but let's just make some comments that computing the integral over the surface of curl of f dot ds arrow directly, trying to do this directly, looks terrible. I mean, part of it's going to be a mess. It really, there's just kind of a lot of funky things that are going to happen. Just give it a try. Let's also comment that computing, based on Stokes' theorem, the line integral of the boundary also looks terrible. You should just give it a try and see, just apply Stokes' theorem once and see what you get. So look, instead of that, instead of computing this integral or doing this integral, what Stokes' theorem tells us we could do, we can apply Stokes' theorem to this and pick a new surface. So what surface do you think we're going to use? What surface would be nicer to deal with, let's say, that has the same boundary as the previous surface, the one that's described up here? Well, let's do this. Let's let S2 be the surface. The surface 4x squared plus 9y squared equals 36 with z equal to 0. So this is a surface in the xy plane. It's a filled in, oh, I guess technically let's put a less than or equal to there, right? But it's the filled in ellipse in the xy plane. And then what we're going to do is compute the double integral over this new surface, S2, curl of vector field f dot ds instead. Okay, it's going to be less work. So the picture I have in mind here is x, y, z. So there's this, let's see, by looking at the equality version of this, looking at x4, let's just, off to the side here, sorry, this is small, 4x squared plus 9y squared equals 36. We can find intercepts 3 on the x-axis, 2 on the y-axis. So there's this ellipse here that's filled in, but it's completely flat, yeah? As opposed to the surface that's being described here is like a popped version of this that lives on top. But that's just the normal vector for the orientation, which just works out to be really annoying for that. Here instead, we have this surface that we traverse around counterclockwise when looking from above, okay, because the original surface was oriented upwards. So then we have this counterclockwise nature here, and then for this new second surface, then we should still orient upward. And the great thing about this new surface and orientation for the surface S2 is much nicer. It's way easier than an orientation for the original surface. The original surface, as you move around on that object that looks like, you know, like a football stadium, or an eggshell, I guess is what it looks like, right? Like everywhere you move around, there's got to be a different normal vector. But that's for S1. For this new surface S2, um, the normal vector that gives the orientation, it's just 0, 0, 1 everywhere, because it's completely flat and level and parallel to the xy plane. In fact, the filled in ellipse we're talking about lives in the xy plane itself. So now we're going to need the curl of f dotted with n, but check this out. N is this, and so the fact that we have zeros in a couple spots, right? We've got a zero times, when we do the dot product, 0 times whatever plus 0 times whatever. That's good. This is really good information for us. I mean, all we're going to have because of those zeros right there is we end up with just the k component, right? So we get just the k component. It's like, yeah, we should be computing a bunch of things, but since we're just going to get the k component of the curl, let's not work so hard here, right? So a lot of the stuff is going to be multiplied by 0, which essentially means it goes away. And so what we have is, okay, I, j, k, and a lot of this stuff doesn't matter. What we just need to look at, because if we only get the k component, we don't need to do I times whatever or j times whatever. We're going to cross out this last column anyway and look at the partial derivative with respect to x, partial derivative with respect to y of, and then we need components of f, so the y and the x squared. Oh, good. We literally don't have to deal with this monstrosity here at all, which is fantastic. Yeah. So what we end up with is something times vector I minus something times vector j plus, and then if we work out the 2 by 2 determinant here, so partial derivative with respect to x of x squared is 2x minus partial derivative with respect to y of y is 1, so minus 1k. Again, there are things going on here in the curl of f. The curl of f is messy. There's a real messy first component, a real messy second component due to that. But the point is that we're going to take the curl of f and we're going to dot it with the n vector, which in our example here is the 0, 0, 1 vector. And so when we dot, all we're going to get is 2x minus 1. That's real nice. That while there's messy parts here, they're not going to actually appear in a significant way in the integral. So we end up with the double integral, so the integral over the surface, the original surface, okay, of curl of f dot ds. That's what the question asked about. But instead of computing this, we use Stokes' theorem. And so we do the integral over the boundary of this, sorry, it should be a line integral. A line integral over the boundary of the surface. We could have put a capital C there because I think we may have already somewhere written C is equal. I guess we didn't. Should have done that back here. C is the boundary of the surface S originally described in the problem. Okay, of f dot dr. So we could compute this, but instead of even computing this directly and turning that into a dt integral, we apply Stokes' theorem in the reverse direction and look at the integral over the new surface S2, the nice flat filled in ellipse, which is much nicer than the popping, eggshell of the ellipsoid. And we have curl of f dot ds. Just trying to get you used to the book notation. It's actually more convenient for us to be thinking of double integral over the surface S2 of curl of f dotted with n d and then a plane s. And the point is that this is going to be the double integral over S2. Let's not work too fancy yet. It's just the key thing to point out is that the dot product of this vector field here with this nice 0, 0, 1 vector is only going to give you that third component. So we're just going to get a 2x minus 1 in here. That's fantastic because the original vector field just looked really awful. So then what? So over the surface 2, um, we we should do some work here. And so this integral is going to convert into the following iterated integral, but a little commercial break off to the side of where this is going to come from, we would need to parameterize S2, right? So the parameters, a parameterization of S2, so S2 is parameterized by R of u comma v is equal to, let's think about it. So this shape there, right, that we need to parameterize, well, look, the third component is easy. Let's just block things off a bit here. The third component is 0, yeah? But we would normally have like a u cosine v and a u sine v to talk about and do something like u going from 0 to 1 and v going from 0 to 2 pi to talk about a filled in circle in three-dimensional space. But we've got an ellipse, so we've got to stretch in the x direction by 3 and in the y direction by 2. All right, and then so then here's the parameter domain information. Okay, and then if we look at RU cross RV, this will end up working out to be 0, 0, 6u. You should work out that detail. ds is going to work out to be 6u times du times dv. So we'll replace the ds here with 6, so sorry, it's 2x minus 1, 6u du dv. U goes from 0 to 1, v from 0 to 2 pi. Ooh, this doesn't work quite as is. I mean, it's not incorrect, but there's an x there. Yeah, we're going to need to replace the x. And so I'll have integral 0 to 2 pi, integral 0 to 1, quantity 2 times, and then x gets replaced with 3u cosine v, 3u cosine v, then a minus 1, close parentheses there, 6u du dv. We won't actually continue with this problem any further, so I'll just do dot dot dot. You could. The real point is you could. It's not a lot of work, but just to save some time, really, right? The whole point is because of how strange that third component looked for f, this problem really would be terrible, and this problem would also be terrible. And so we somehow got lucky to convert this into a nice problem. So for an interactive question, what I'd like you to think about is the following. So describe the technique of using Stokes' theorem twice in the same problem, right? So please note that 3 different integrals are involved. Three different integrals are involved. So what I want you to think about is with those 3 integrals, what is each integral over? What shape, right? So what shape is each integral over? You're integrating over a surface here, you're integrating over a curve there. What's going on, right? So think about those things, and then specifically answer this thing, and how are the shapes related?